Indeed. There's slide 1. Do you want to wear this or you want to stop at the podium? You need to be like within range of it. That podium much further back than this. You know what I mean? And you just advance with those arrows at the bottom into the middle.
Okay.
Forward, backward.
Okay. Well, now I guess we'll get going. So I'm Ricky Beamer, and I'm here today. Ooh, gotta be real close. Okay. So I'm Ricky Beamer, and I'm here today to present on the comparison of IV&V's use of non-verification environments and the program's use of verification environments. And Miss Katie Warner was my intern this summer and helped me generate a lot of the content in this presentation, but she is back at school and unable to be here today. So these are the general topics I'll be talking about. First will be a very high-level overview of the IEEE 1012 standard, and then a little bit of some of the reasons why IV&V wants to retest these environments. We'll also have an overview of the MPCV program and the developmental test environments we have on site, and some of the test environments that are available to the program that aren't here. Then I'll talk about how test cases were retested and our process results and some future work. And I'm sorry for the sniffles. I've been battling the cold the last couple days. Okay, so the IEEE 1012 standard is the standard for system and software verification and validation. This standard puts forth a set of guidelines to determine whether the development products conform to the requirements and its intended use. This standard is, by and large, what drives our IV&V program here. It outlines that the verification and validation processes include system, software, and hardware, as well as all interfaces. And it applies to these systems. So Annex C of the standard specifically calls out what is independent verification and validation. And for the purposes of this presentation, I've bolded some of the text. So it states that for sharing of tools is allowable for system simulators where an independent version would be too costly to develop. And for these shared tools, IV&V will conduct qualification tests to assure that the tools do not mask errors in the systems under test. And then due to cost and schedule, as well as the nature of the first flight for MPCV, IV&V did not conduct full qualification tests on the provided testing environments. We did execute supply checkout scripts to assure that our simulators and the program's counterparts performed in a similar manner, and this strategy has been used on other IV&V projects where full qualification was not practical. So kind of really what Ms. Warner's project was this summer was to go through and retest a lot of the run for record procedures that we've encountered already. And a lot of this was to see how precise and accurate the development environments we have on site compared to the big brothers that are certified testing environments. We also wanted to see if any anomalies did occur or surfaced, and if they did, that would direct us to do some specialized testing to see if it was the flight software that was at fault, if it was or if it was the simulator that was at fault or if it was the tester at fault. It's kind of a murky triangle. We are also trying to see how we can use these tools in the future and on future missions, and provide greater confidence in the testing that we have done previously. So up till now, so I like to cook, and I'm going to relate this presentation a bit to cooking. So up to now, I've kind of described an overall meal that I'd like to serve sometime in the future. And now I'm going to do a little bit of a deep dive into a specific dish, starting with some of its ingredients. So first off is the multi-purpose crew vehicle, which is essentially NASA's replacement for the space shuttle. It is based on the Constellation program's Orion design. It will be capable of conducting regular in-space operations such as EVAs and science missions with payloads delivered by the Space Launch System, which is currently in development for missions beyond low Earth orbit. Actually, here's a nice picture of it. The MPCV vehicle is the front teardrop shape of this, and then you can see the kind of the conceptual design of the European service module behind it. Yeah, so the Exploration Flight Test 1 mission is scheduled to launch on December 4th of this year, so a little less than 3 months from now. It will ride atop of a Delta IV Heavy rocket, launching from Kennedy Space Center in Florida. It will do 2 orbits, and on the second orbit, it will swing around wide to simulate a deep space reentry. And it will land somewhere off the coast of California. Okay, so now to introduce a few more ingredients. The first is a development test environment called Socrates, or Software Only Crew Exploration Vehicle Risk Reduction Analysis Test Environment Simulation, which even for NASA, that is a really big acronym. Yes, it was developed by Lockheed Martin for the purpose of flight software development testing and verification procedure development. It has 3 main components. The Socrates controller, which is the user front end, and it also facilitates communication amongst the other components. The flight software, which the controller allows us to load in multiple versions of the flight software for testing. And Orion Sim, which is a key component that contains the Earth models that the vehicle will be flying through, as well as some of the basic hardware models. Ultimately, the flight software will reside on a vehicle management computer. And Socrates emulates the vehicle management computer through use of Wind River's Symix software, which is a software-only model of the hardware processor. And not on the slide, but one version of Socrates allows us to execute unmodified flight binary in order to increase the fidelity of the system. Okay, the next one, or the next environment that we have here is Plato, or Partition Level Application Test for Orion. So it is a software-based execution environment developed by NASA at the Johnson Space Center, which unfortunately the slide has John, but it's Johnson. It allows users to interact with the flight software partitions at their sampling port boundaries. So the MPCV software kind of is picking up some elements from the commercial from the commercial aviation industry, in that we're running a partitioned environment. So each partition, or if you think of the whole flight software, the whole processor is kind of a loaf of bread, each partition is a slice. And partitions are the boundaries between the slices. So the sampling ports allow communication between the partitions, but if a partition were to disappear, the whole software doesn't stop functioning, at least not until, well, there's compound failures, but so MPCV uses these sampling ports for communication of commands, reporting of telemetry and statuses, as well as basic software responses. So the simulation environment is similar to Socrates in that it runs on a Symix environment and allows it to use unmodified flight software. One additional feature of Plato is that it allows us to stop the software every minor frame. So this means that we can trace how data is flowing from the time it is received by the antennas to where it ends up in flight software and then trace the response back. Okay, so Plato and Socrates are developmental test environments. They're not meant for certified or run for record data. The verification test environments include the Vehicle Management Computer Test Bench, the Integration Test Laboratory, and the Assembly Test and Launch Operations Center. These facilities allow for hardware and software to be integrated and tested together. And these facilities will have flight hardware or flight-like facsimiles, and they allow for risk identification and to mitigate those risks so that the mission will have a better chance of being successful. Okay, so I've essentially introduced all of my ingredients to this dish. Now I'm going to talk a little bit about some of the steps that we use to make it happen. So the first is how we selected our test cases. We went through and examined the available test procedures that the program has developed. And then we examined the available run for record data from the certified test environments. We went through and correlated the two to make sure that what was tested is what is reflected in the results. And then from these, we were able to prioritize the test cases for what suited our needs the best. And this included a general system test, as well as several test cases where we were trying to establish the fidelity of the developmental environments. So then our next plan was to go through and execute the test cases. And in several situations, we did have to modify them just slightly in order to get more specific data that we were looking for without having to dig through tons and tons and tons of data. And then lastly, we were going to go through and note the differences between the two. So this was essentially our process. We went through and re-executed the run for record test scripts. And again, some of them we had to tinker with just slightly. We didn't change any of the core components, just added a data extraction process. We knew that the run for record data we were looking at was from older flight software versions. So as the flight software matured, certain bits of it were going to change. This is primarily with the telemetry packet numbers, and even some of the very basic dynamics would change based on how the data was loaded and what models that they chose to use for that particular build. So kind of taking that information into account, we looked to see if the data captured in our test results was closely matched up closely with the run for record results. So here's kind of our results. With Plato, we ended up rerunning 32 test cases. And of these, 25 of them correlated very closely with the program's environments. 7 of them did not. And through a little bit more digging, we discovered that the flight software, one of the models in the flight software had been updated somewhat substantially. And the test scripts that we ran were designed for the pre-modified flight software. Since this presentation has been generated, we've been notified that those scripts have been updated and they're essentially ready for us to retest. Then with Socrates, we reran 12 test cases. 10 of these corresponded or were very consistent between the run for record and ours. But 2 of them were not that close, like not close enough for us to consider them consistent. Doing some initial data process with this, it is looking like these were in systems where, or the test scripts were testing systems that the flight software didn't model very well. The fidelity wasn't there. But there's still a little bit more digging that our team has to do in order to confirm that. So results, I talked about the top 2. So overall, our use of the Plato and Socrates developmental environments will support meaningful flight software testing for our test cases without having to depend on the program for execution or test analysis. For the EFT1 flight, we are not convinced that the developmental environments are suitable for final testing, but we do think that with a few more modifications and a few more tweaks, the fidelity will be there for at least a certain class of requirements for future missions that these environments could be used for run for record testing. So where do we go from here? Well, as I've already said, we need to dig deeper into the couple of test cases that weren't consistent. Also, since this has been generated, we've gotten a new flight software build that will go through and re-execute the majority of the test cases in this that I talked about here. Also, in December, we'll have the launch, and then shortly after that, we will be able to get the actual flight data. Here, we'll be able to go through and compare the runs for Plato and Socrates against the real flight and see just how, see what the fidelity actually is of these systems. This will allow us to establish the strengths and weaknesses to know where we can go in the future. Additionally, with the actual flight data, we'll be able to go through and examine any of the anomalies. We want to see, essentially, could Plato and Socrates have detected these in some type of test case previously, meaning that could it have been prevented. So this is a big area that we'll probably spend most of next year working on. And with that, that is the end of my presentation. So any questions? Yes?
So on your test models, the test cases that you use, as the software developers are making changes, I'm assuming they're using a software configuration manager software. Does that trace to the requirements for every time software is changed? And then does that trace back to your test cases so that you have preventative analysis capability to understand what test cases are impacted?
So I must say mostly. There are a few cases where we found where that wasn't the case, where we weren't, the tracing wasn't properly there. By and large, they are doing a fairly good job of, if they modify the flight software, that's noted and everybody's made aware of it, and then the test owners can go through and update their software as needed. What we're running in, another issue we're running into right now is time. This, again, this flight is happening fairly soon, and at least to get a run on one of the certified test environments is really difficult at the moment. So it's being traced by and large. But again, there are a couple places where it hasn't.
Just a quick question. I think it was slide 14 with your deviations. You went ahead, you executed your test script. Your deviations you felt were due to an outdated test script, so you went ahead, updated your test script. Did you rerun and it passed through?
So we have not had time to rerun it just yet. So with the Plato side, we know that that was the cause of it. I think it was last week, I was made aware that the scripts had been updated, and I just haven't had time to get to it yet.
And you capture all that in your documentation as well?
Yes, yes.